Hi everyone, my name is Major Steve McCarthy, and I will be introducing to you the decision-making phase of the STP for the next 3 lessons. Today we're going to talk about introduction to the decision-making phase and also performance modeling. This is just where we are as a bit of a review for the course. Decision-making phase, one more phase, solution implementation after this one, and we'll be complete with all the requirements as far as lesson objectives are concerned for this course. Today, these are the 6 lesson objectives that we'll cover, starting with understanding the tasks included in the decision-making phase and going into modeling, performance modeling, and simulation techniques which could be useful as we gather data and also as we score our alternatives. So, as a bit of review or a bit of an overview for the decision-making phase, is important to note what the input is. And we just finished solution design phase where the output was candidate solutions. That becomes the input for decision making. The output for this phase is solution decision. Over here on the right hand side you can see some key things that go into the decision making phase. The highlighted in bold or the italicized in bold words indicate the tasks that are required in the decision making phase, starting with value scoring and costing, going into sensitivity and risk analysis, and then improvement and trade-off analysis. And we'll go over these in detail in this lesson and the following lessons. One thing that I would just like to highlight in this lesson is that we are still using value-focused thinking. We'll talk a lot today about value and how it compares to cost and how this is one of the first steps that we can or that we should pursue in making recommendations to our stakeholders. So, before we get started in all this, we need to ensure that we have a good baseline. And what I mean by that is we need to conduct a review of all the 2 previous phases of the STP in preparation to score our alternatives. So after being done with solution design, we know what our alternatives are going to be. We'll have screened out the ones that don't meet our minimum criteria. But we have to review all the data from previous phases to ensure that the raw data going into our alternatives is the correct data that we should use. This is indicated in page 396 to 398 of the textbook, but in addition to revising the problem statement in preparation for scoring, we also need to ensure and validate our value model, our candidate solutions, our life cycle cost model, our modeling and simulation results. We need to confirm our value measure ranges and weights, and having done all of that, we'll be prepared to score our alternatives. So before we get into that and some methods that we use to score alternatives, I'd just like to re-ground us on the problem that we're looking at this semester, namely the response to the possibility of coronavirus resurgence at USMA. So here's one of the functional hierarchies that we've come up with. Lists the 5 high-level functions, some objectives and some value measures to achieve those functions underneath the overall fundamental objective, which is to protect USMA. After we've done that, we identified what our values are and what our functions should be. We've created through alternative generation and idea generation some options. And here are 5 options that we've come up with in response to achieve the problem statement that our stakeholders have explained to us. But you'll notice that it's the question at the bottom there, how do we get the raw data for the value measures? It's often the case that we create alternatives and don't have defined ways or concrete ways to get raw data. Or we do have concrete ways, we just don't know what they are. So the textbook outlines 5 scoring methods which will be used. And those scoring methods we can use in order to get data for our options 1, 2 through 5. So one way to get one way to get data for our different alternatives is through the use of operational data. And operational data is really historical data or numbers that exist from pre-existing systems that are very similar to ours or similar to the alternatives that we're generating. The pictures here that you see are examples of a car problem where we're trying to score different vehicles so that we can pick the best one that meets our stakeholder needs. And over here what you see is operational data. Perhaps this lady that's driving is showing us the time that it takes to go from 60 to 0. Perhaps she's braking for someone in the road. That's data that can be gathered through numerical information that exists in open source areas. Another way to get it is through testing, and testing is a deliberate process wherein we put, in this case, vehicles through a specific set of tests to get very calculated results. So this would be like a crash test where we can determine the speed at which a vehicle or the impact due to passengers in the vehicle when it crashes at a specific speed. You can probably also test for braking speed, just like up here. Another method that we could use is simulation. And we'll talk about simulation and modeling a little bit more later on, but simulation is a computer representation of the actual system. It's a lot less expensive than testing would be. And you can imagine that we can run this simulation hundreds of thousands of times and not have to create a new vehicle every single time we simulate a crash. So there's benefits to that. Another way that we can get the data is through mathematical models or other types of modeling. And then the final one is through subject matter expertise. So if we don't have information or we don't have data on a particular value measure that we need, we can always ask someone who is familiar with the system or similar systems, is familiar with that particular value measure, and we can say, hey, what's your best guess on what the time from 60 miles an hour to 0 miles an hour would be under these conditions? And that person would tell us. So those are the 5 value scoring methods that we use to gather data. Let's say in this class, more than likely you'll be using either operational data, because this can be gathered from various sources, or subject matter expertise, where you ask someone that's familiar with the system and they can give you the data in order to fill your value model or additive value model, so you can determine overall value scores. So we're going to dive a little bit deeper into the value scoring method of modeling. Page 99 of the textbook defines a model as an abstract representation of a system, and a couple pages later it defines why we use models. The bottom line in all of it is that they're flexible, they save time, and they save money. Similar to the benefits of using a simulation, models can achieve the same effects. There are many different types of models. The first one is a physical model. This is probably what comes to your mind up front when you think of a model. You think exactly down here of a model helicopter. You have, of course, this model helicopter can be used to simulate or to model the effects of wind, perhaps on the aerodynamic systems of the aircraft. You could use modeling to simulate the effects of wind on a bridge, and then modeling we use all the time in tactical situations where we build terrain models so that we can simulate a operation or a particular event occurring in combat environment. So those physical models are used quite frequently. One thing to note, though, is that they can be expensive. It can be pretty expensive to conduct experiments on through building prototypes or through building model vehicles or systems. The other one is a graphical model, and this, as you can see here, the trusty value model from our SDP, that is a type of graphical model. These models are used to provide stakeholders with a visual representation of some aspect of the system or multiple aspects of the system. They can be used, we use the SDP, for instance, in showing stakeholders how their value for a particular value measure will change with a range in raw data. And this can be extremely useful for them to get a grasp of where they stand in, or how that value, what that value really means to them. The next one is a mathematical model. You can think of the additive value model as a mathematical model. There's a linear program over there in the top left, and the velocity mathematical model. These are used, well, the additive value model we use, of course, in this class, but we probably won't get into more complex mathematical models in 301. So as far as the characteristics go, there's 4 different characteristics of a model: purpose, time, randomness, and variables. And within each of these characteristics, we have 2 different categories for each. For purpose, they can be either descriptive or prescriptive. For time, it can be either static or dynamic. For randomness, deterministic or stochastic. And variables can be either discrete or continuous. For purpose, as the name implies, a descriptive model is one that describes past events, historical information, whereas prescriptive could predict some aspect about the future. The model that you see here for descriptive is overall weekly Iraq attack trends. So this uses historical information to show a visualization of the trends as they occurred in about 3 years. Now this could also be turned into a prescriptive model, where if we said that our current place and time was November of 2007, we could use this model to make predictions about the future, perhaps extend it out to our current time and show our stakeholders how based on previous attacks, we can expect X number of attacks at these times in the next couple months. So descriptive models can be used and can be manipulated, or at least the data that's underneath them can be manipulated to be prescriptive in nature. But prescriptive models are those that make some prediction about the future and can help stakeholders in their decision making so that they get the optimal outcome. Timing consists of static and dynamic. Static meaning that it does not change with time. Dynamic meaning that it does change with time. Dynamic model here this dynamic model that is represented here is of weather patterns, which of course changes over time. And then this picture right here is representation of the flu virus, which does not change over time. For randomness, there's 2 different categories. Again, we have deterministic and stochastic. Deterministic being that there is no randomness at play, that the output will always be the same. Y equals mx plus b is a common mathematical equation for the slope of a line, and this will always be the same given the inputs m and x appropriately and b appropriately. Y will always be the same. Now stochastic means that there is some variance in the output. Say for instance I took this deterministic model, and instead of using m as the slope, I used some random number and said that m can be some number between 1 and 50 or whatever, any number between 1 and 50, which would be a uniform distribution. Then I could inject randomness into this model. But stochastic, the picture here is the flipping of a coin. We don't always know the outcome. We know what it could be, one of 2, but there is randomness at play for whether or not we're going to get heads. And lastly, variables for discrete and continuous. The textbook does a pretty good job of explaining the difference between discrete and continuous variables, but discrete has a set number of outcomes, a finite number of outcomes, whereas continuous can have an infinite number of outcomes. Thinking about cars, for instance, there's a discrete number of vehicles that can travel through this Easy Pass station in a given time frame, or there is a finite number of vehicles that can be packed into this area at any given time. Since there can't be half of a vehicle or a third of a vehicle, this is number of vehicles is a discrete variable. And here, when we think of like miles per hour or time from 60 to 0 seconds, braking speed, that is continuous variable because there's an infinite number of possibilities. Miles per hour can be 50 miles per hour, 50.1 miles per hour, 50.11, 50.11, 1,000 miles per hour. There are any number of variables that can go into that can be the output or the outcome of that value measure, for instance. So it would be a continuous variable. So putting all these together, we have what's known as the modeler's toolbox. And the modeler's toolbox is just all the possible combinations of whether or not the model is static or dynamic, deterministic or probabilistic, descriptive or prescriptive, or discrete or continuous. There's 16 total combinations of these four characteristics. So here are some qualities of some useful models. I'm not going to read them all in detail, but just think as you're building your model, or as you're attempting to, or telling your stakeholders or your modelers what you need or what you need out of that model, it should have these 7 different qualities. One that is pretty important, and there's a trade-off or two that are important with a very distinct trade-off, are simplicity and accuracy. Now, all of our models, we want to be simple because we want people to understand them. We want other modelers to use them in the future and to give us output when the situation changes or when the problem changes. We want to be able to use the same model. However, we also want that model to be accurate. And there's a trade-off between simplicity and accuracy, in that those models that are extremely accurate, that are near perfect, are not very simple. Unless we're referring to just a very simple system in general. If we have a complex system, which is what we do in this class, we either model it very simply and have a trade-off with accuracy and give some of the accuracy away, or we model it very specifically and in a complex way, and it becomes extremely accurate. So that is something that needs to be decided between the systems engineer, the modeler, and the stakeholders, whether or not we want to achieve extreme accuracy. For some systems, having extreme accuracy is probably important. Thinking about NASA systems, for instance, in one of the case studies the other day we talked about the REACH, and that is probably one of those systems where we need to be extremely accurate. Therefore, our models will not be simple; they'll be extremely complex. There are other cases though where a simple model will do, and our decision makers could benefit from the model, whether or not it is 100% accurate. So as a segue into trade-off analysis, I'd like to talk a little bit, or bring us back to this coronavirus example, refresh our memories about the 5 options that we have for a response to the coronavirus resurgence. Last lesson we talked about cost and net present value. And so for every alternative that we have, we're going to determine what the net present value is for that alternative. And using modeling and other techniques to score our alternatives, like we talked about, we'll be able to achieve a value. We'll be able to find a value using our additive value model. Put together, these things can provide a very useful visualization that shows a trade-off between cost versus value. So these are arbitrary numbers. I just made them up for cost and value. But we can see that when plotting them, when plotting cost against value, we can see how all the options compare to each other on both the spectrum of value on the y-axis and the spectrum of cost on the x-axis. So what is trade-off analysis? Well, it allows us to combine the output of all the other tools that we've talked to this point and all the other tools we need in order to create the total value, or to understand what the total value score is. And it allows the analyst to discuss what trade-offs to make. So there are some cases where high value but very high cost might be okay, but there are other cases where we want a lower cost, and we'll give some of our value away to achieve a lower cost. The other thing, and probably the most important thing that this trade-off analysis shows, is what our dominant and our dominated alternatives are. So similarly to the coronavirus example and plotting the different options in the cost versus value, here's some arbitrary example of 3 alternatives and their costs in millions of dollars. So when we look at these, we can see that the blue square achieves a higher value than the yellow triangle. However, it is extremely, or a lot more money than the yellow triangle. And the red diamond achieves a lower value than the blue square and a higher value than the red diamond, but it's more expensive than both of them. And this is an important distinction. If a solution is more expensive but provides less value than another alternative, we say that that alternative is dominated. If there is more cost and less performance, an alternative is dominated. So in this case here, alternative 2 is dominated by alternative 1 because alternative 1 has a higher value for less cost. So we always rule out the dominated solutions. There's no reason to consider the dominated solutions in sensitivity analysis or in trade space analysis, which we'll talk in the next lessons. We should just eliminate this alternative altogether because it does not achieve what our stakeholders, our stakeholders are not getting the value that they could get from another alternative, but they would still be paying more money. So this solution could go away. Another example here shows that this blue square is less value than the red diamond for more cost, and again shows that there is a dominated solution, and it is dominated by the red diamond, which has a higher value for less cost. So going back to the coronavirus example, we can see using this that option 1, 4, and 5 all achieve lower values than options 3 and 2, but option 4 and option 5 are more expensive than option 2, and option 1 is more expensive than option 3. So option 1 is dominated by option 3, and option 4 and 5 are dominated by option 2. So the two choices that we should continue to assess to determine which one is the winning solution would be options 3 and option 2. That concludes this lesson. Next lesson we're going to talk about sensitivity and risk analysis. See you then.